production demands precision measuring. Parts manufactured in widely separated factories must be completely interchanged. This necessary uniformity is assured and controlled through every operation by accurate measuring equipment. From blueprint to finished assembly, precision measuring is the guide to perfection. For precision measuring, the skilled accurate tools produced from quality materials, carefully manufactured and rigidly inspected to ensure lasting dependability. Accurate measuring tools in the hands of skilled mechanics result in work approaching perfection. But precision has not always been associated with measurement. At the dawn of civilization, linear measurement may have been considered only in terms of the distance man could travel in one day, or the length of his reach. As time went on, and man conversed and traded with his fellow men, the parts of the body such as fingers, hands, and feet became the unit of measurement. Long before Christ, the cubit or forearm was one standard of measurement. This was the basis of measurement for such famous structures as the Great Pyramids of Egypt and the Parthenon of ancient Greece, structures which have lasted to modern times. Less than 900 years ago, King Henry I of England set a standard yard as the distance from his nose to the tip of his extended finger. 3 barley corns, round and dry, was the more or less accurate standard for the inch established 3 centuries later. It was less than 100 years ago that the British Imperial Standard Yard was established as the basis for the yard we use today. A duplicate of that yard is kept in the Bureau of Standards in Washington, and this copy is carefully maintained at the L.S. Starrett Company to assure accuracy of its precision tools. The machinery of the past did not demand great accuracy. Most parts were custom made, and a fraction of an inch one way or the other made little difference to satisfactory operation. Wooden parts could be made to fit close enough on this old lathe made of wood. Of course, it would be a little difficult to cut an accurate screw thread on this machine, but such a problem did not bother the mechanics of 100 years ago, when most of their measuring tools were made of wood. The machine age brought the need for greater accuracy. And today, rules are so essential and so frequently used on a variety of work that they are made available in a wide selection of sizes and markings. They range in size from as small as 1/4 inch in length for measuring in grooves, recesses, and keyways, to as much as 12 feet in length for accurate measurement of large work such as this casting. Steel rules are graduated in the English and metric systems. Many of them can be obtained with varying graduations on each edge of both sides, and even on the ends. Some rules are graduated as fine as 1/64 of an inch in fractions or 1/100th of an inch when marked decimally. Key seat rules are handy for drawing lines parallel to the axis of round work. A depth gauge is used to determine the depth of holes and recesses in jig, die, and fixture work. With a protractor head, it can easily be used for measuring an angle or chamfer. The slide caliper is especially useful in taking frequent, quick measurements. A fixed jaw on the rule and a sliding jaw provide contacts that bear against the work. Clearly visible markings indicate both outside and inside reading. A thumb piece facilitates quick setting, and a convenient locking screw operated by the thumb holds the moving jaw securely. For the correct measurement of long length, a steel tape with a hook is a necessity. The combination square, one of the most useful of all tools, may be used as a square to mark off or align work, or to lay out a 45-degree miter. A protractor head may replace the square head for laying out angles of any degree. The hardened steel rule may be graduated in 8ths and 16ths on one side, with 32nds and 64ths on the other. The heads are available in smooth or checked finish. To reverse the rule in the square or center head, release the lock washer and rotate a half turn. This patented feature automatically positions the lock bolt to receive the rule. A Starrett level mounted in the head comes in handy on many jobs. Combination squares have many uses. Here, a fixture base is checked for squareness, and the shoulder for the accuracy of its 45-degree angle. A combination square may be used as a depth gauge to measure the depth of a shoulder. For layout work, a centering head has been substituted on the rule for the square head to locate the center of this round piece of work. A double protractor head is helpful in layout work, as it can be used on either side without resetting. When center punching finely scribed lines in layout work, this hammer with a built-in magnifying glass is of great assistance. Calipers are used to measure distances between or over surfaces, and for comparing dimensions with a standard, such as a graduated rule. When calipers are held lightly by the fingers, it is possible to feel extremely slight differences in dimension, as on this lathe mandrel. Transfer calipers are valuable in measuring the depth of recesses and over flanges. They have a fine adjustment for greater accuracy. When feel shows that the correct size is reached, the nut binding one leg to the auxiliary leaf is loosened, swung out to clear the obstruction, then moved back against the stop where it will show the exact size measured. Then and now, the rules were read directly with more or less accuracy depending on the eyesight and carefulness of the user. Present-day production brought the need for more accuracy. The dimensions of parts produced by mass production methods must be controlled to close tolerances so that they can be immediately interchangeable. The vernier invented in 1631 by Pierre Vernier is a combination of steel rules which permits exceedingly accurate readings. A graduated bar has a fixed jaw on one end. A movable jaw slides on the bar. The adjusting jaw may be locked and the carrier jaw moved by an adjusting nut. When adjusted, the carrier jaw can be locked. A graduated plate on the carrier jaw is compared to the fixed scale on the bar. Dividers can be accurately set by inserting one leg in the hole on the preset carrier jaw and adjusting the other leg to seat in the centering hole on the fixed jaw. One side of the vernier caliper is marked for reading outside measurements, while the reverse side is adjusted for inside measurements. The fixed scale is graduated in inches, and each inch is divided into 40 units, each of which is equivalent to 1/40th or 25,000th of an inch. Every fourth division is numbered, the first being 1 and is equal to 1/10th of an inch or 100,000th. 2 is 2/10ths of an inch or 200,000th. 3 is 3/10ths or 300,000th, and so on. is graduated so that 25 graduations on the plate occupy the same space as 24 divisions on the fixed rule. If the zero line on the vernier plate corresponds with the zero line on the fixed scale, all other graduations are out of line except the 25th division, which is a full graduation short of the 25th line on the fixed scale. Thus, each space on the vernier plate is 1/25th less than each space on the fixed scale. 1/25th of 1/40th is 1,000. Therefore, the first space on the vernier plate is 1,000th less than the first space on the fixed scale. Two spaces on the plate are 2,000th less than two spaces on the fixed scale, and so on. If the vernier plate is moved so that any graduation lines up with a graduation on the fixed rule, that number of thousandths is added to the distance between the jaws. In this case, it is 15 thousandths. Let's take a reading of this workpiece and figure it out.